Corentin, Bayet y Bruno Pujos present SpeedPwning VMware Workstation. The speakers share their journey in reversing and hunting for vulnerabilities in VMware Workstation for Pujos in only 2 months. This ended with a race against time with writing a VM escape exploit in less than 10 days with one vulnerability that didn't provide much primitives.
Hi everyone, welcome to our SpeedPwning VMware Workstation talk. Also called failing at Pujos but doing it fast. Little introduction, what is this? This talk is about the research we did for Pujos targeting VMware Workstation. So we wanted to share our methodology, our technology, and a funny story about this research. We have a lot to share, so please don't be scared by the amount of slides, everything will be fine. As doing the research, we might go fast, so there is some parts that lack of details, but we'll be pleased to answer any question you have during the live Q&A or even after, on Twitter, for example. But first, who are we? So I'm with Bruno.
So hello, researcher at Synactive, and I mostly work on low-level research, such as UEFI. And I'm with Corentin.
Yeah, I'm Corentin. I'm also a security researcher at Synactive, and I previously published about Windows kernel heap exploitation. So we are both interested in virtualization technologies, and in 2020, Pujos came back with a virtualization category. So we are very interested to participate in the contest on this category. But we had only 40 work days to score, so it's 20 days each, which make 4 weeks. And we finally picked VMware Workstation because it's our favorite desktop virtualization software. The target was previously documented, and it seemed doable in a limited time. We already work on some components, but never on the workstation. So this is the planning we are trying to follow. And the first half week was dedicated to the discovery of the target. Then we wanted to do 1 week of fuzzing setup to make the furthest run for the following 2 weeks, because we are in holidays or we had conferences to attend to. And finally, we had 2 weeks of full vulnerability research and hopefully with some exploits. But first, I will let Bruno speak about the discovery of the targets.
So, like Corentin said, we're familiar with virtualization, but for people who are not, the basic idea is the virtualization software will emulate the hardware of a computer. And it's mainly used to run different operating systems on the same hardware. So there is 3 interesting parts in a virtualization software. First, we have the guest or virtual machine, VM, which is the operating system which runs on the emulated hardware. Then we have the host, which is the main operating system on the computer, which runs on the real hardware. And finally, we have the hypervisor, which is all the code for handling the guest. On a security point of view, the host should be isolated from the guest, and the guest should be between them. Finally, what we are trying to find is a VM escape, which allows to get code execution from the guest to the host. So, like I said, it separates the hardware from a real computer, and a big part of that are the devices. So devices can be anything from the network card to the hard drive to the graphical components and so on. And they use traditional technologies, hardware technologies, such as PCI, DMA, and so on. And today, the emulated devices are the main attack surface from the guest. So now let's talk a little about Workstation. So in this schematic, you can see the different components. So first, we find our guest on the blue part, and on the bottom part, we have the low-level part of the hypervisor, and on the top right part, we have the part which interests us the most, the VMware-VMX part, which is a user-learned program. There is 1 per VM, and it contains most of the components of the devices which are emulated by the hypervisor. So the first thing we did for when starting this project was localize the user input. So with functions which allow to register callbacks and the IO ports, mem.io, PCI, and so on. Also all the functions which allow to read, write, or map the memory from the guest. And then we search for all the debug symbols all the symbols we could rename. We did a lot of scripting for that. And basically we could rename a lot of globals from the setup of the configuration. There was a lot of debug strings. We also found the code for loading the snapshot was really useful. And we were also able to do some signature from the OpenVM Tools project, which is an open source project developed by VMware, and we were able to find some symbol for log functions. Finally, there is two interesting parts which help us at the beginning. So there is a dash debug program which has more debug strings, so it was helpful at the beginning, but when doing the actual research, we didn't use it because it contains more checks. And the second thing, there is a paper called Straight Outta VMware by Census Lab, and which documents all the initialization of the device, and it was really useful. So now what we wanted to find was a VM escape, and we had to choose some targets. So we had some constraints because of Pontoon. Our guest and our host must have been Windows 10, and they have to be with the default configuration. And on the other side, we wanted to focus on only one binary, so the VMX, the userland program. And so we chose only device which were implemented in it. So we chose three of them: the USB, because it looked complex and there was vulnerabilities in the past; the audio, because we didn't find any previous work on it, and we thought there may be some parsing in it, so it seems interesting; and finally the SVGA, which was a little like USB. We knew vulnerabilities in the past. It was a little documented. So now let's talk about the vulnerability research, and Corentin will present our first results.
So yeah, we're gonna jump quickly to the results of the vulnerability research. So unfortunately, we'll present the outcome of the research of the HD audio and XHC device, along with the fuzzing results. So unfortunately, we don't have time to go too deep into the details. So I will just present the outcome. So HD audio first. We quickly understood why there were no prior work on it. It's because there is very few code, and it's only forwarding all the raw data audio to the host. So we were able to reverse all the code. It was not interesting. On the second part, XRCI, so is USB 3. There is a lot more code than HD audio, but most of it is unreachable without plugging specific USB devices, which is out of scope. And so we audited partially the reachable code in the default configuration. We found one useless bug that was patched since because it was supported, but no exploitable vulnerabilities. And on the fuzzing part, so we spent a lot of time trying to fuzz every component we edited. So both with WinRFL and Synactive's internal fuzzer, which is a fuzzer in-memory fuzzer. But hyper-very hard to fuzz, so it was time-consuming and very hard to implement. And at the end, we had the fuzzer were not very efficient, and we had no result at all. So we have big regrets spending way too much time trying to fuzz some code we just could have reversed. And I will let Bruno speak about the SVGA device and the research on it.
So SVGA2 is a device for the graphical interface. It's not a real device. There is no actual physical device which exists. It's an idealized version of the hardware, and it's made for being as fast as possible. And because of that, some part of the implementation will be only enabled depending on the host, the guest, and the configuration. When we look at it, so we took the default configuration and we look only at the 3D part of the API. There's also a 2D part, but the 3D part seems more complex, and we wanted to focus on that. So there is two papers which are really interesting. The first one is written by people from VMware, which actually how they designed the SVGA2 device, and it's really, really interesting. The second one is the Straight Outta VMware paper. I talked about it before, by This from Census Lab, and it was great. It's a reversing engineering approach, and it explained a lot of things which are really interesting and help us a lot. So what does the device look like from the guest point of view? We have a PCI device which registers 3 ways for the guest to send data to it. So first we have a frame buffer in the middle of the schematic, which is a classical frame buffer and was not really interesting to us. Then we have at the top an interface through IO ports, and at the bottom an interface which is called the FIFO interface. Both of those allow to access registers, which are used for configuration and initialization and stuff like that. And they both allow to send commands to the device. So for the IO part, it's called the command buffer interface. it's the FIFO command interface. So using this command, we can create objects. And so this is graphical objects, and the objects are everything we usually see. So surfaces, vertex, and so on. And when an object is created, the hypervisor will read the description of the object from the DMA memory zone in the guest, lazy load it in the VMX. And because there can be synchronization problem between the hypervisor and the guest can actually ask read back from the hypervisor, and in that case, the VMX will copy back the memory in the DMA zone. So on the VMX side, all those graphical objects are stored in a structure called ArrayID, which is basically just an array with function for adding, removing, and searching. And what's interesting about that array is it's the further array in charge of handling the memory, so doing the allocation and the thing. And each graphical object, one array for each of them. So now let's get back to the command. So you can send one command, a batch of commands at the same time. And the commands allow to define, to create, manipulate objects. There is actually several APIs which are not always enabled, depending on the configuration, on the host, and the guest. For us, we use two of them. So the GB one, which we suppose means global, which is the one which seems to be always enabled, whatever your host is. And we use the DX one for DirectX, which is specific when we have a Windows host. For the DX API, there is a few interesting points. The first one is all objects which are created using the DX API are associated with a DX context. And that DX context is also a graphical object. And when you send command for manipulating any object in it, it will always be associated with a current DX context. So now objects have been created by the API. They will be given to a backend, which is called the renderer. So in our case, it will be the DX11 renderer, but that depends on configuration. We did not have actually time to reverse it, but we will use it later. And so those objects are translated in other objects, which we call resource container. And those resource containers can be used to make the transition to the real DirectX API from Windows. So now we were at the end of the research, and we still did not have a vulnerability. We were at the end of the 40 initial days we had for finding a vulnerability. And luckily, like just 14 hours before the end, we actually found it. And so now let's talk about this vulnerability. So the vulnerability we identified was in the handling of the context. And because when you send the command for the DX API, you will want to precise which context is used. There is a global variable, which we call current DX context, which gets the current context. So let's look precisely how that works. So like I said before, we can send commands in a loop, in a batch. So there is actually a loop for executing all the commands. And during the initialization of the loop, it will first get the DX context ID from the guest, and we'll check if the context actually is already existing on the VMX side. If it's not, it will create it and add it to the array ID, which will also allocate it. Then, when he has the DX context, it will set it in a global current DX context, which point on the same allocated region. Then, when we look with the DX command, we'll use the global current DX context, and we can actually mix up this command. So in this schematic, there is only DX command, but we can also use GB command in the middle. It's not a real problem. And finally, at the end of the loop, the global will be unset, and it will be set to null. There is a command called dx invalidate context, which actually deletes the dx context from the array ID, and because the function from the array ID are in charge of handling the memory, the object will be free. And the problem with that is that if the dx context we destroy is also used by the global, there is no check made on the global, and the current dx context will still point on the freed memory. So we got to use after free. So how does that look like? So initialization of the loop didn't change, but if the first command we send in the batch of command is the dx invalidate context, it will delete the dx context from the array ID, which will free the memory. And then the next dx command will use the global, which still points on the free memory. at loop, the global is still unset, so we have only the command of the same batch, which can be used for exploiting the use after free. So what can make us leave this loop? So obviously there is no other command, but also if a command fails, it will go out of the loop. And there is an asynchronous event system, which is called action, which is actually shared between the VMM and the VMX part of the actor. And if one of those actions is triggered, we will get out of the loop. So we did not reverse this at all, basically, and it create problem during the exploitation. But we will, so yeah. So at that point, we had a vulnerability, so that was great, but we were at the end of the 40 days. There was only 1 week before the registration for Pod2Own, and we already had a POC for triggering the vulnerability. We had an interface written in Python for communicating with the HVGA2 device, but it was not great. There was a lot of things missing, and we didn't have time to reverse a lot of things. We had no idea what most of the commands do. We didn't reverse at all the backend, but like, we have a use after how to exploit, right? 2 hours in ZTF. Well, we are only at the middle of the presentation, so you can guess it's a little harder than we thought. And so now let's talk about exploitation.
Yes, so just as Bruno said, we found the vulnerability at the very end of the research, so there. And we had for only like 10 days to exploit it before the registration 2.2. And so as we were very tired, we decided to take the weekend off, so these 2 days there. And obviously, what are you doing when you are very tired to rest? Well, you probably do some sports and sprain your ankle. Yeah, this is because exactly what I did. Yeah, it was not a very good call, actually. But yeah, so after this very, very relaxing weekend, we started the exploitation. So we had like 5 days to the deadline registration. And we had 10 days before the deadline where we have to send everything to ZDI. And the goal was to have the working exploit, so at least a proof of concept at the registration deadline. So we have time to work on the reliability of the exploit and on the setup, because we had some work on the setup too. So on the strategy part, this is Pod2Own. So we need to demonstrate the exploit by popping a character exe or notepad.exe to demonstrate the exploit. So the simplest way to do that is to call winexec with the first argument pointing on control data. So to do that, we need at least a leak of the base of VMware-VMX process to know the address of the import table. Then we need an array read to read the address of a function of kernel 32 to compute winexecs, and finally to jump on winexec. So there's probably a better way to write the exploit, but we didn't have much time to make a better one. So the problem we said we have no time is that UAF DX context is really bad to have in user free. There's almost no pointer in it, and they are not used to read and write data. Its size is 5b68, so it's very big, but we have no time to reverse out the backend, so how its use or the fields. So the only thing we know we can do is roll some D-words by using DX commands. And the only strategy based on this is to reuse a chunk in use after free, reject, and use the DX commands to overwrite some values in the new object. And with the help of heap messaging, we might be able to control the alignment with the chunk in use after free to precisely target which fields we want to overwrite in the target object. So we did some heap messaging. So the segment heap is not enabled. So it's a classic anti-heap, which means every allocation under 3FFF will use low fragmentation heap if used enough, so LFH. And we don't want at all to use LFH because heap messaging is very hard in it. So fortunately, the use after free object has a size of 5b68, so it will never be handled by H. So we can actually do heap messaging. But we need a messaging primitive to do that. Fortunately, again, the SVGA device provides the perfect messaging primitive with the set GB shader command. So we can create GB shaders, and it allows us to have a fully controlled allocation, so controlled size, fully controlled data. It can be freed or allocated at any time, so it's perfect. So it's a technique that was previously described in 2018 by Zizis and straight out of VMware paper again. And then we need to choose a target. So there is not much of it because as we said earlier, they need to be bigger than 2FFF. You want to target it to avoid LFH. Time to reverse, so to search for perfect objects. So we just use what we knew that exists. And the GB context has a size of 5490, so it will never use LFH. And it's a good target because the ability to read back a part of its content, so we can copy some part of the structure back into the guest. So by overlapping with a new F chunk that contains pointer, it would be a way to leak some pointers. So it's a very good target, actually. And finally, the vulnerability can time, so with no problems. So we can obtain different primitives with it. And using just this strategy, we successfully obtain three primitives. First, a heap pointer leak on an arbitrary free and arbitrary call primitive, both with some constraints, but they were enough to get everything we need to exploit it. So let's see how. We'll do a review step by step of the exploit, and we'll start with how to get a heap leak using the user stuff free.
So yeah, the first step was to get any pointer. And the idea for that was to read back mechanism for being able to read back the pointer from in the guest. So the thing was the readback command for the DX context could not be used because it did not use the global in which was the pointer. So we had only, because of that, we had only two possibilities for using the use after free. The first one was to leak a pointer, which was stored in the DX context using another object readback functionality, or to trigger another memory corruption, which would then allow us to have a leak. So obviously the first possibility seems the best because we have to have another step. And so at that point we were like, okay, so we want to do that. Wait, do we have one pointer in that object? So we actually found one pointer in that object, which is a pointer on a DX shader object, which is another object. So that's not the same shader Corentin was speaking before. Those were the GB shader, and so this one is for the DX API and are not the same. The thing about so it will also be in the array ID, but the actual content of the buffer will also be allocated in the heap, and the pointer is also stored in the DX context object. So if we could leak this pointer, that would be great because it would give us a leak in the heap. And because we control the content of the shader, we could choose the allocated size. And so we could have a leak in the heap we want. So that seems really, really great. And we wanted to do that. So how do we do that? So first step is to create a DX shader. So there is a command DX set shader, which will do that for us. And it uses a global current DX context. So we could use it with your use after free. So that was great. And the fourth step for when adding a shader are done by the VMX as this one. So first it will fetch the DX shader object from the guest. Then it will read the content, the actual content of the shader from the guest, and both of those will be allocated in the heap. Then it will check that the content of the shader is actually valid. And finally, it will check the shader is not present in the associated DX context. So when adding a DX shader, the two first steps are really classical. That's the same for all objects, but we needed a correct content. So the DX shader format use something called the SML4 format, which we have the structure in the Gallium header. So that was documented a little. But when reversing, we noticed there was actually two main parts. So first part, which is the array of tokens, and which is the main part of the shader, and a second optional header with three arrays of objects, and we don't know what they are. We still actually don't know what they are. And the great thing about this is the verification was really minimal, and we could hardcode all the content of those arrays and the second header. And so using this second header, we could have a shader of 3C18, which was perfect for getting a leak into the NT heap. So now we have the shader, and we need to read back the pointer from the DX context, and we could use for that the GB context Corentin spoke about before. And it was a perfect match because the position where the DX shader pointer is right, the DX context is a position back from the GB context. So that way we didn't have a lot of messaging to do. There was one little problem on the first step. Adding a DX shader, it will check that the shader is not already present in the DX context. And for that, it will actually try to get the DX context from the array ID. So it will use for that the array ID find value function. And that function, if the context is not in the array ID, which is okay because we have removed it for using the use after free, will return null. And so because it returned null, a little later we had a null dereference. So we wanted to avoid that, but the thing was, it was pretty easy because we actually reuse the DX context with the GB context. And so the actual ID which will be used will be the ID of the GB context. And so we just had to have the same ID for the GB context as the one for our valid. So what does that look like step by step? First, we will fill some hole in the paying for avoiding problems. Then we will allocate two contexts, context A and context B. Then we will trigger the use after free for the DX context A. Then we will reuse it with the GB context, and we will use the ID B, the same one as still valid DX context. Finally, we trigger the creation of the DX shader using on the DX context in use after free, which will void the pointer in the GB context, and we will bypass the null dereference problem because we have a valid DX context also. And finally, we can read back the GB context B and get our pointer. So for doing all of this, we have triggered the use after free and the DX context. We reuse it in the context. We void the DX shader pointer on the use after free DX context and use the read back functionality of the GB context for getting the pointer. So we successfully triggered the leak and the heap, and it was actually pretty great because the memory could be clean. By removing the DX context B, it will also remove the DX shader, so no problem here. The size of the DX shader is partially controlled, and we could get a leak in the heap of our choice. We had some constraint on the content, but it was okay. And we could trigger it several times if we needed, so perfect. We were pretty lucky on that because it was the only pointer the DX context, and this pointer does not seem even used. So it seems just to be like a dead pointer on that object. But at that point, we had pretty much used up a lot of the 5 days where we hoped to have a working exploit. So we had the heap leak working, we had the global strategy for exploitation, but we were not having at all a full exploit. And on the Friday, Workstation decided to release a new VMware decided to release of Workstation. So, but we will come back on that later. But we still decided to register because we were pretty confident we would have time to finish before ZDI. And so now let's speak about the next steps.
So yeah, while Bruno was working on the heap leak, I was already working on the next step, which is getting a leak of the text section. So to do that, I was just simulating the heap leak using the debugger. And yeah, we need a leak of the text section to be able to control the execution flow. But unfortunately, we didn't find any way to do that using directly the use after free of the DX context. So we needed a second stage. So we leveraged the first use after free, the one of the DX context, to reach an arbitrary free primitive. And we use that to turn another object after free, and we use that to finally get a leak of the text section. So let's see how. So the GB context object can be linked to another object called resource container. This object are stored in a global array, and to link the GB context to the resource container, there is no pointer. The GB context only stores an index in the global array called RC index at offset 4. The idea is to use the US after free of the DX context to control the RC index of a GB context, and with the set depth on state command, we can write the offset 4464 of the DX context, and we can use heap messaging to align the offset 4 of the GB context with it. So how does it look like? We're gonna massage the memory with GB shaders. So we're gonna allocate alternatively some chunks of size 5b68, which is the size of the DX context, and 3t98. We freeze the first one, and then replace it with the DX context. We can then use the vulnerability to put it in use after free. And the free chunk, we can reuse it and split it with another GB shader. Finally, we can freeze the last GB shader because the two chunks freed are next to each other. They will coalesce into one big chunk. And we can finally allocate a GB context in it. And with this setup, the offset 44 of the DX context perfectly align with the offset 4 of the GB context. So then we can use the set depth on state command to rewrite the RC index of the GB context. And by freeing the altered GB context, we can reach a function called svgr destroy GB context versus container with the controlled LC index. So we can reach this function with the controlled LC index. And the first thing done here is to fetch the GB context versus GB context versus container from the global array using the index. And because we can control some data in the global section, we can the pointer. And thanks to the heap leak provided by what Bruno just explained, we can fully also control the field B220 and the differences from it. So we can reach the function svga callback and destroy with a controlled argument. So we can fully control the object here, which there's a certain interesting thing in this function. First, there is a loop that allows to do an arbitrary call. And we cannot use that for now because we don't have anything to call since we don't have a leak of the text section yet, but we will. But for now, we can just keep this loop by putting 0 in the NB callbacks argument and reach straight to the end of the function where there is an arbitrary free primitive. At the end of the function, the RC backend structure will be freed. So this is a constraint because we need to have a valid chunk here or it will crash because there is some checks. And finally, the last part, the RC pointer will also be freed using an internal heap. So we also need to fake a header and use a real chunk to avoid crashing. So the idea is to use the arbitrary free primitive to get a text leak. So to do that, the strategy is to put a GB context after free, and we'll then make it overlap with an object that contains a pointer to read back. And this object is the actual GB context versus container, so is the object we are actually faking. And its size is B7 is 0, and there's a function pointer at the very end of the structure. So how do we do that? Again, we'll message with so we'll spray blocks of B840 bytes. We'll then free the second one and split it with a GB shader, we call it shader 3, and then allocate a GB context at the end. So this is a target GB context. This is the one we want to put in use after free. And then we want to free the first allocation of B840 with other. So we want to have a setup like this. So one shader, two shader, and a shader we call shader leak. So this is all GB shaders. And using the heap leak that Bruno explained before, we are able to leak the address of this shader. So if this works, we have all this in memory. We can fully control the data of the GB shaders, and we know where it's located in memory. So now we can build GB context with this setup. So the idea is to make the resource container points into shader 1. Then when it will fetch the field B220 and the references, so field B220 will fall right into shader leak, and the reference will give the value of the very start of shader leak. So we can reach the function svgr callback and destroy with the address of shader leak. So it's a shader that's got the data in it. 0 to skip the loop for now in the NB callbacks field. Go straight, and we just have to put RC backend callback args to the value of the GB context. And when this code path is reached, the GB context will be put in use after free. Then the shader leak will be put in use after free. And in the parent function, the RC pointer will also be freed. So the shader 1 will also be freed. So it's not a problem at all to have shader 1 and shader leak in UAF. We can just reallocate it. Actually, we want to keep this setup, and shader 2 is there. Shader 1 and shader leak don't coalesce because if they were next to each other, they would coalesce. So what we want to do then is just to allocate shader 1 and then we allocate shader leak. So we keep the setup. And we can finally free shader 3, and the two free chunks will coalesce, and we can allocate the GB context versus container. And this will write the pointer to the text section into the GB context in UAF, and we can finally read back the text pointer. So yeah, to sum up, we triggered another use after free of the DX context. We reuse it with the GB context to be able to fake a GB versus container in memory. And we use that to reach an arbitrary free to put another GB in UAF. We use an actual GB versus context versus container and use the GB context to get the pointer. So now we can do the last part of the exploits. So we want to reach the exact same path, and to do that, we just need to reallocate the GB context. We use the set distance state command to again control the S. Exact same setup, before, as you can see, we can reach again the function svga callback on this time. We have a leak of the text, so we can use the arbitrary call. So in this loop, we can see that we the number of counts, the pointer that is called is always the same, so it function that would be. But the arguments of the function, we control it also change between each call. So it's very interesting. And the things we have to know here is that is obviously at a location in the heap. So we know the address where the callback pointer is stored. So this is important for the following of the exploits. But yeah, the ability to do arbitrary calls, this is really cool. We were reaching the end of the exploit, but wait, there's actually control flow guard enabled, and we completely forgot.
So yeah, it was Saturday afternoon, and suddenly we can actually call a function, but well, we call everything we want. So how does CFG actually work? The principle is like when there is an indirect call in the program, it will check that the call is made to a valid function. And what is called a valid function is any function in the binary which can be called indirectly. For making the actual check the address of the call and compare it with the bitmap. This is implemented in NTDL. So we were pretty stressed at that point, and we wanted to find a solution quickly. So what we did was we scripted everything. We dumped the bitmap in debug. We re-implemented the check in Python. We put all of that in IDA. We gather a list of all the functions we could actually call depending on the bitmap. And at that point, we had an arbitrary call, but we still did not have any way to read of an arbitrary memory. So we looked for small functions which would allow us to do that. And we took only the function which deref pointer and which had no loop and without any call to other functions. And quite quickly, we were able to find two functions which interested us.
So yeah, using the scripting, we are able to find two functions. So the first one, we called it arbitrary read-write, simply because it will take the value for the first argument is a pointer. It will dereference it to get a value and write it on the value of the second pointer in the second argument. So we can write memory with it. And the second one is almost the same. It will take a 32-bit value from the first pointer in the first argument, but this time it will add it to the destination of the second argument. So we can arbitrarily increment values. So with these two functions, we have the ability to read and write in memory. We have also the ability to do annihilation, and we actually have the ability to fully control the execution flow because we know the address where is stored the callback pointer, where it's called loop turn. So we can use the read-write primitive to change the value of the function pointer and switch the function between each loop. So with these three primitives, we also actually got a Turing machine, and this is really pretty cool because we can just now chain calls to finally call winexec. So how does it look? So this is the heap at a known location, so we can use it to store values in it. And the first call will be a read-write call, and we'll simply read the import table where there is the address of create process and write it in the heap. So then we have the address of create process somewhere in the heap. We want to switch the read add function, so we'll read the address of the read add function in the heap and write it on the call pointer. So our next call is a read add function. We want to use that to read the offset between create process and winexec function and add it to the create process function. So it becomes the address of the winexec actually. We want to go back to the read-write function, so we'll do the same thing. We'll read the offset between the read add and read write function and add it to the call pointer. So we are back to the read-write function. And we can finally read the address of winexec, write it on the call pointer. So our last and next call is winexec using notepad as argument. So to sum up, we use the same steps than before to fake a GB resource container in memory. And we use that time to chain not so much while calls and turn this into a Turing machine using the text and a heap leak, and finally call winexec at the end. So there's a quick demo if we have might have the first video. Okay, thanks. So yeah, we're going to check the version of VMware, which was the last at the moment of the point one contest. So our exploit is in a self-exploiting archive you want to launch as administrator. And after a while, it will just spray a bit of memory and then hopefully pop a notepad on the host. So this is the exploit when it works. Thanks for the video. And yeah, so we had a working exploit, but we had some setup to do before the contest. And we had only a few days to do that. So I will let Bruno speak about the last rush.
So yeah, it was Monday morning, and I wake up and I see Corentin had actually got a notepad. So I'm like, oh, great, we may have actually a chance to do this. And we spent some time trying to test the reliability of the exploit. It was not perfect, but it seemed okay. We did not have any setup for testing. So basically, when we say we tested, it was we launched just the exploit 10 times and see how many times. But have a lot of time before the contest, and 4 days before, VMware released actually a new version of Workstation, and we just had a look if the vulnerability was still present, which it was, but we didn't have updated or set up because we wanted to finish the exploit first. But of course, like if you are running the exploit on the new version, the vulnerability is still here, it will obviously work, right? Well, not really. So it's Monday, and our exploit didn't work on the first version. And on the Tuesday, at the end of the Tuesday, we had to send everything to ZDI. So we were pretty stressed. And so we spent some time in thing, and we found out that the heap leak didn't work anymore. And so we looked at why, and they actually added some parsing on the DX shaders. So it was not related at all to our exploit, except that we need it for the heap leak. And basically what they added more check, and we could still use the same technique, but the size of the DX shader we could register using only the second part of the second header of the shaders was way lower. And so it changed all of our messaging. And at the end of the Monday, we had something which worked, but not often, around 30% of the time. And we had only 24 hours before we had to send everything. So on the last day, we tried to fix the reliability of the exploit and to do some tests. But once again, all tests were made by hand, by just launching the exploits one time after another. And but we didn't have more time. We had to do the setup, so we had written everything in Python, and we did an executable file, Py2exe, and a self-executable archive for creating a .exe. And we had to change how we interface with the kernel in the guest, because we actually use debug mode from Windows in the guest, which was not possible during Pujos. So we had vulnerable sign driver and change stuff like that. And for all of this, we asked the help of two of our colleagues, so Wakfu and Lucas Georges, which helped us a lot for this. And well, thanks to them, we were able to finish in time and send everything to ZD. And now we are going to speak about Pujos.
Yeah, so finally we can get to Pujos. We are a bit confident. We are really exhausted, as you can see on the picture. And if you can have the second video, you will see how it went. So as you might have seen and heard, I was a bit upset. So yeah, it was a failed attempt. The exploit failed 3 times in a row. So we had numerous in the exploit we knew about. We could have fixed it sometimes, but we did not. But of course, we don't know exactly why it crashed on the D-Day. So it's a bit frustrating. But anyway, ZDI bought the vulnerability on the exploit outside of the contest. So that was really, really cool from them, because we did not work for nothing. So really cool. And yeah, a bit of feedback on really well organized, even with the COVID situation and everything in remote. And they answered quickly to our many questions, the conditioning of the exploit, because we are. And AI does everything to make your exploit work. They wanted us to succeed, even if. But AI was great. To conclude, with almost 2 months working as much as we could on this project. We found several bugs. The one we just talked to you about, we exploited. One hardly exploitable that we reported to ZDI outside of the contest, and multiple bugs useless. And next for next time, 40 days is really not enough for this kind of project. We'll let the fuzzing aside and just do more because it was more efficient. And yeah, fast spawning was really challenging. It was frustrating at the end. It was, but we really enjoyed working on this project, and yeah, it was awesome. And this is the end of our presentation. So thank you very much for everyone for listening us. And you can find us on the live QA session right now, or if you have any question, we are available on Twitter also.
Yeah, and we finally have time.
Thank you.
Thank you.